Yeah, so I'm Tom. I'm a PhD student here at Monash, working with Daniel Price and Christoph Pant on kinematic sensitivity of embedded protoplanets with X-Farmer. I'll try not to keep you from your lunch for too long. So the first thing to know is that planet formation occurs in disks around young stars. So here I've got a bunch of images of 5 disks around young stars taken with the Atacama Large Millimeter Array, or ALMA. And these are 2 different kinds of images. So on the bottom, we have millimeter continuum, and on the top, it's integrated intensity of 12CO line emission. And so these are sort of probing different components of the disk. And so for also some scale, these things are a few hundred AU across. And you can see that the continuum emission is coming from these like smaller parts of the image. So the 12CO is probing the gas component of the disk, which is sort of big and fluffy and held up under pressure. And the millimeter continuum is more coming from sort of like the mid plane of the disk, where from like dust grains that have settled, since they don't really feel the pressure as much, like mostly larger dust grains. And you can see in these images lots and lots of substructure. So we've got these like rings and gaps, and some other structures like a little arc thing here. And in the top ones, you can sort of see some evidence of some spirals. And so most commonly, these are interpreted as evidence for planets having already formed in these disks. And so the question for planet formation becomes, can we constrain the properties of these planets to try and, test our ideas of planet formation? And so recently, the one very useful way to find these planets is through disk kinematics. So traditional methods for finding exoplanets don't work so well in a protoplanetary disk because of the big amount of disk material that is in the way. So transits don't work, there's a disk. Radial velocity doesn't work, there's a disk. So direct imaging has got some promise, but in the same time, the disk is much brighter than the planet, so finding the planet is very challenging. So what we can do instead is use the ALMA interferometer to take observations of line emission. This is 12CO, the 2-1 rotational line, and use the Doppler shift of the line to measure the velocities in the disk and look for a perturbation that's caused by the gravity of the planet acting on the disk. And so what I'm showing here is a typical, it's called a cube of these images for the disk around HD 163296. And on the left is scanning through velocity. So each one of these images is a slice in velocity of the disk. And then on the right, kind of, if you like integrate over the velocity direction, what does the total disk look like? And so I've put them side by side so that you can get some intuition for the fact that you are sort of scanning through the red shifted to the blue shifted side of the disk, or maybe it's the other way. But and yeah, so in 2018, Christoph found these little wiggles in this channel here, which is basically been interpreted as a deviation away from smooth Keplerian rotation, and has been associated with a planet in that region of the disk, sort of like with the gravity stirring up the gas. So here I'm showing a phantom simulation of a planet embedded in a gas disk, and you can see that there's spiral density waves and shocks that are excited by the planet, which propagate out through the disk. And the region nearby the planet is where the perturbation is the strongest. And so that's sort of interpreted as what's causing the kink in the channel. And so coupled with the radiative transfer code, Christoph showed that you can accurately reproduce the morphology of this feature with planets' exciting density waves. So I'm part of the ExoAlma Large program, which is a comprehensive planet hunting campaign in the sub-millimeter, sort of the first of its kind to take really deep observations and look extensively for these kinematic signatures of young planets. And so there's 15 sources in the sample. And yeah, so we're looking for still forming planets with disk kinematics. And so on the bottom, I've got the typical plot that every exoplanet talk has, with the population of exoplanets, as well as a bunch of sort of like proposed planets that have been interpreted from substructures in disks, as well as the stars are from kinematics, as well as the two ones that count as confirmed. But the main thing here is, well, what about non-detections? So for instance, in high contrast imaging, when we look for planets in disks, you can calculate the contrast that you would expect for planets of different masses and use the fact that you haven't found anything to constrain the population of planets. And so what I want to do is a similar thing for kinematics, where we can calculate the sensitivity to planets that we should have found if they were there, and use that to constrain the overall population by ruling things out. So the overview for my project is basically, to find a way to quantify the kinematic sensitivity to embedded protoplanets, and then use that to create statistical constraints on the protoplanet population. So here's a messy slide. So the point here is to show you the features of one of these observations, where these are all of the different images taken at different velocities or different frequencies. And if you pick a particular pixel and look in the velocity direction, what you'll find is something that looks like one of these, where mostly you have nothing, like for instance in these channels, and then you'll have a peak for where that pixel is the brightest. And that's sort of like the location of this peak should be interpreted as the velocity of the disk in that pixel. But to complicate this picture, since the disk in the gas component is flared, the 12CO emission comes from like a layer quite far above the midplane, and so there's a top surface and a bottom surface illuminated by the central star. So in these images, you can see that there's kind of like a curve here and a curve here, and the back one is the lower surface. So when you look through these line profiles, you get this contribution from the lower surface and from the upper surface with two different velocities, because they have different line of sight velocities. Unless, of course, the disk is basically face on, and then you'll only see the front. And so the typical thing to do to get the velocities of the disk is called spectral collapse, where you try to like incorporate all of these images down into one image and take some quantity. So the thing that you would want for kinematics is velocity. And so this is called a peak velocity map. And basically, you just take for every single pixel the velocity that corresponds to the peak. And so the better way to do this, rather than just to take the bin with the highest intensity, is to actually fit functions in the spectral direction to every single pixel. So for here, maybe you would want to fit the sum of two Gaussians, and one Gaussian is going to be the front surface, one Gaussian is going to be the back surface, and then the center of the Gaussians will be the velocity of the disk in that pixel. And so people have done this to make even better velocity maps, but so far no one's sort of like used this to quantify the uncertainties. So it's kind of expensive because there's like hundreds of thousands of pixels, so you've got a lot of fits to do. And if you're fitting a double Gaussian to each pixel, well, it's hard to do that robustly because the peaks can be on top of each other. And since the velocity is kind of the thing that we want to constrain, that's what I've been working on. So the first thing that I've done is I'm using Hamiltonian Monte Carlo to fit two component line profiles to every single pixel. And the reason that we're using Hamiltonian Monte Carlo is because, unlike traditional MCMC, you use gradient information from your likelihood function. So I'm just using a Gaussian likelihood. And that lets the fit proceed, or the sampler basically, be very, very efficient. And so we can get through our hundreds of thousands of pixels very quickly. It's also a lot more robust to choosing your initial guess. So like you don't have to choose a very good initial guess, which is very good, because first I tried this with just like affine invariant MCMC, and it's a mess. It doesn't work. So now that you've fit a line profile for every single pixel, the uncertainty that you get on the center of the peak is the uncertainty in the velocity for that pixel. And so that gives you a map that looks like this. So this is the velocities in a disk from the epsilon sample and the uncertainties on the velocity. And so this is in meters a second, which would be good if I wrote that on there. But So you can see that we're doing quite well here. The 1 sigma uncertainty is around like on the order of 20 to 30 meters a second in most places. But this isn't really the whole story, because in every single pixel, I've assumed that all of the fitting that I'm doing can be assigned exactly to the center of the pixel, which is not true. In reality, these images have a finite resolution, which is larger than the pixels, and it's basically the synthesized beam from imaging with your interferometer. And so you need to account for the fact that the inference that you make shouldn't actually be assigned exactly to the center of the pixel. You have a spatial uncertainty. And so to try and incorporate this, I've done sort of like a bit of like a heuristic approximation kind of thing, where, so the one-dimensional version is you say that you have some rotation curve for your disk, and if you're uncertain about where you are radially, you get an inherent uncertainty in velocity, right? So for a 2D map of the sky and the velocities on the sky, you can do an equivalent thing where you basically use the gradient of the line of sight velocities to calculate how, if you screw up on the sky a little bit, how much you screw up in velocity. And so that gives you a map that looks something like this. So this is a radius of 100 AU in the disk, and then this is the uncertainty that you get from beam size of, didn't write it, but like a particular beam size. And you can see that for this, it's more on the order of like hundreds of meters a second towards the center of the disk. So, and that's how it varies with inclination. So if the disk is very face on, this effect is minimized. And if the disk is very edge on, then you do worse. And so if you can combine these two components, you can make, calculate the total sensitivity. So this is for 2 disks in the sample, HD135 and lit calcium 15. And so in the left panel, I've got the contribution from the spatial uncertainty. And you can see that as you go to smaller radii, this basically explodes, note the logarithmic scale. And then in the middle, we've got the uncertainty with radius from the line fitting. And so basically in all cases in the sample, we're completely dominated by the uncertainty from the finite beam size at small radii, and not really until you get to really the very far out radii where the rotation curve of the disk is very shallow, does the uncertainty from the line profile fitting really kick in at all. So these two are added in quadrature to make the total uncertainty. And yeah, basically you can see that this looks a lot like this and not much like this. And so there's two trends that you can notice as well, which is basically the main result that I have so far, in that if you decrease the beam size, so you increase your spatial resolution, this goes down, but this goes up. So when you're imaging interferometer data, you get a bit of a choice as to what size you should make your beam. And so this is increasing spatial resolution. It actually makes your line center uncertainty worse because it makes your image noisier. And so just to conclude, we've developed a method to calculate kinematic uncertainty, and we found that so far we seem to be dominated by the spatial uncertainty in the image. And so even deeper observations would allow us to make images with smaller beam sizes and higher sensitivity. Yeah, so the to-do is basically to use this to constrain the protoplanet population.